Okay, zeros of polynomial functions. We know what we mean by zeros. We know what we mean by polynomial functions. And in a way, this is repeat of Algebra 2 stuff. I'm not sure there's much new in this. So there's two different theorems that they give us at the beginning. One of which we definitely use and we teach this stuff, which is called fundamental theorem of algebra. But if you read the fundamental theorem of algebra, you don't quite get the sense of how we use it, right? I mean, the fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than n is greater than 0, then f has at least one 0 in the complex number system. Okay, not exactly what we take from it, right? Let me do this. Right, what we take from it is this. A polynomial with a degree equals n has n complex zeros. And when you kind of combine it with this one here, linear factorization theorem, it kind of puts it together. Other places they'll say, well, there's a corollary to this fundamental theorem of algebra that basically tells us this. But in fact, whatever's the degree, if it's a fourth degree polynomial, it has 4 complex zeros, right? You just look at the degree, that's how many complex zeros, right? We're not talking about real zeros, right? Real numbers are a subset of complex numbers. Some of our complex numbers will be, zeros will be real. Some will be imaginary, right? They'll add up to whatever the degree is. Right? The linear factorization theorem says that if you've got a degree n, then you've got n linear factors, right? And a linear factor just means x minus a 0. Whatever is the 0, let's say C1 is a 0, then x minus C1, that's a factor, right? Because what would you plug into this factor right here, x minus C1? What would you plug in for x to make it equal 0? C1, right? So C1 minus C1 is 0, right? That's why C1 is the 0 itself. The linear factor is x minus the 0, x minus C1. So put all this together, and it kind of says that for a polynomial of degree n, you expect n complex zeros. Okay. We good? You okay? So, for example, hardly worth the board space, but how many complex zeros would you expect in the first? Right? The degree is 1, so there is 1, 0. How about the second one? Right? The degree is 2, 2 zeros, complex zeros. Right? How about the third one? 3, 3 zeros. And the fourth one, 4 zeros. I mean, pretty often on the test, I'm going to put a question that says, it doesn't say find the zeros. It just says how many complex zeros, how many real zeros, how many imaginary zeros. Right? So the first part, how many complex zeros, that's easy, right? It's the degree. Okay, now, the rational zero test, we got a bunch of these tests and theorems and things like that. The rational zero test is specifically getting at zeros that are rational numbers. What do we mean by a rational number? No, that would be a real number. What is a rational number? Come on, we can't be struggling with this thing you've been taught for years. Fraction. Rational means fraction. It means any number that could be written as a fraction is a rational number. So we're looking for zeros specifically that are rational numbers here. And this is, again, the way it's worded, you may have a little bit of a trouble trying to understand what it says, but the application of it's actually pretty easy. It's saying if we have a polynomial, right, which has a degree of n, because the first term is x to the n, right, and it's got these coefficients, right. The first term is, we're just calling it a sub n, which is just a general way to denote a coefficient, right. So you've got all these terms in the middle, and the last term is a constant, a to the 0. Okay. If there are rational zeros, right, they are going to be some combination of the factors of the constant term divided by the factors of the first coefficient. This P and Q, right? They're calling it P and Q, but the P basically is the factors of A0, factors of AN. So the factors of the last term divided by the factors of the first term, the first coefficient of the first term. You take all those fractions. It doesn't mean all of them are zeros. It means if there are rational zeros, they have to be in that list that you create. And you know, this edition of the textbook seems to have done it a little bit different. And I went with it. It's okay. I'm not sure it's a huge improvement, but the very first examples they do, the leading coefficient is 1. So if you're doing factors of the A0 divided by the factors of 1, then basically it's just going to be the factors of the last number. That's it. So find the rational zeros of each function. We're going to do it one at a time. And I have to say, I mean, this is an exercise in doing something that is, maybe it's a little bit obsolete with today's technology. But in the old days, this is exactly how we had to do it. Take, for example, the first one. If we're going to find rational zeros, then we're going to make a list of all the possible factors of 8 divided by the factors of 1, right? So factors of 8 divided by the factors of 1. Okay, well, what are the factors of 8? 1 times 8, 2 times 4. But actually, if it's 8, it could be -1 times -8 or -2 times -4. So whenever you see the factors, they're always going to be plus or minus. It's never not plus or minus, right? It has to be. It has to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And then the factors of 1 are 1 and -1, right? Plus or minus 1. So when I take all the combinations of the numbers on the top with the numbers on the bottom, it's basically the list of the numbers on the top. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. No. 1 over 1 is 1. So that's plus or minus 1. All we're doing here, we're taking 1 over 1, 2 over 1, 4 over 1, 8 over 1. And you get that list right there. Okay, again, this is like the way we used to do this in the old days. And I'll tell you that in the book, in their examples, which they didn't do these are the ones underneath their examples. What they showed, they just automatically went to the ones that worked, okay? But how many possible rational zeros do we have in our list? 8, okay? How many actual complex zeros are there in this? 3. All of these are not zeros. At the most, 3 are zeros. At the most, right? So you're going to go through this list, and most of the time, it's not going to work. You're not going to get a remainder of 0. And you just have to try. When I was your age doing this, we would go through pages and pages of checking, and we didn't have a graphing calculator to just kind of like zoom in and, wow, it's going to be right there. We would just do a few until you found it. I mean, you can see that all three of these are cubics. So once I find one, then I'm left with a quadratic equation. And with a quadratic equation, I can always find the last two. I don't need to go through this test anymore. So let's try to do a few here. So here's our coefficients. 1, negative 5, 2, 8. 1, negative 5, 2, 8. Remember synthetic division, right? In fact, let me do this. Edit, paste. Oh, that's wrong. Try this again. Edit, copy, edit, paste. Edit, paste. Oh, that didn't work. I know, but I'm not going to be able to like separate it out. Follow blur. Oh well, I thought I could be clever. Obviously, I can't. Okay, let's go back. 10. 1, negative 5, 2, and 8. And let's just start synthetic division. I'm going to start with a negative 1. Okay. Remember the synthetic division? Bring down the 1. Negative 1 times 1 is negative 1. Add it up, negative 6. Negative 1 times negative 6 is 6. Add it up, 8. Negative 1 times 8 is negative 8. 0. So actually, I guessed. I guessed, and I got it right. So there's 1, 0. These are the coefficients of a polynomial. What's the polynomial? X squared minus 6x plus 8. So, I mean, you could go through and do synthetic division, but at this point, can't you think of how to factor that and find the last two? Right? What are the two numbers whose product is 8 and sum is negative 6? Negative 2 and negative 4. So the last two, x minus 2, x minus 4. So the last two zeros are, x equals 2, x equals 4, which are in our list, right? So there's your 3 zeros. Now, if I would have got to the bottom here and it wasn't remainder 0, I would have just done another one until I found one. Okay, let's try another one. Okay, let's find our, I mean, there will be questions that just say, list the possible rational zeros, okay? For this second one, list the possible rational zeros, right? They're going to be the factors of 4 divided by the factor, or you could say negative 4, but it doesn't matter. The factors of 1, right? What are the factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4, right? How many is that? 6, right? How many zeros will there be? 3 at the most. And they don't all have to be rational either. Maybe one will be and the other two will be imaginary. You won't know. So let's go through and do our synthetic division. 1, 2, 6, negative 4. Okay, what number do we want to start with? Anybody? Try negative 1 since it worked last time. Okay, negative 1. Negative 1, 1. Negative 1, 5. Negative 5, negative 9. Nope, that didn't work. Let's try, what's that? How about 1? Okay. 1, 2, 6, negative 4. Bring down the 1. That's 1 times 1 is 1, 3. 1 times 3 is 3, 9. 1 times 9 is 9, 5. That didn't work. Negative 2. Okay. 1, 2, 6, 4. Negative 2. What's that? Okay, negative 4, you're right. Negative 2 times 1, negative 2, 0. Negative 2 times 0, 6. Negative 2 times 6, negative 12. Negative 16. That didn't work. Let's try 2. 2, 1, 2, 6, negative 4. Bring down the 1. 2 times 1 is 2, 4. 2 times 4 is 8, 14. 2 times 14 is 28, 24. That didn't work. So we've done plus or minus 1, plus or minus 2. It's got to be one of the 4s then, huh? Let's see if I can get some more space by hitting this. Right. So let's try 1, 2, 6, negative 4. We'll try negative 4. Negative 4 times 1, negative 4. Negative 4 times negative 2, 8, 14. Negative 4 times 14, negative 56, negative 60. Okay, and then the last, because that didn't work, let's try 4. 1, 2, 6, negative 4. Bring down the 1. 4 times 1 is 4, 6. 4 times 6 is 24, 30. 4 times 30 is 120, 116. So we did it 6 times and we didn't find any. So what does that mean? There's no rational zeros. Now, what I would really suspect is that I might have made a mistake. Oh, sorry. Go back to this one. Let's try it. 1, 2, 6, negative 4. Negative 1, 1. Negative 1, 5. Negative 5, 9. Okay, try this one. Negative 2, 0, 0, 6. That one's right. 1. Okay. 1, 3, 3, 9, 5. Okay, that didn't work. 2, 4. 2, 4 is 8. Okay, you know, it could be there's no rational zeros. But I mean, I'll tell you that that's what happens sometimes. You know, you would do pages and pages of these synthetic divisions and nothing would work out, but you made a mistake like on the second one. And you had no way to fix it. We do have a way to fix it. Put it in the calculator and check, right? But I'm going to leave it for now because that's what we're going to end up doing on the problems that follow. Okay, let's skip over that one. Now, find the rational zeros of this one. What are the possible rational zeros? Well, what are the factors of 125? One plus or minus 5 plus or minus 25 and plus or minus 125. Pretty sure it doesn't have any others in there. Let's see. Ooh, it should have, no, 5 times 25. Now, I don't even remember exactly, but I think my intention at this point was to say, let's not just sit there and go through these lists. Your first starting point will be, let's put it in the calculator and see if we can find where the rational zero is so that we can divide it out. So go to the calculator, right, and put in that function, clear, and it'll be x to the third minus 15 plus 75 minus 125. And if I graph it, do you see any zeros there? You know, I can't hardly see what's going on there, but I suspect that maybe 5 is a 0. Definitely it's not negative 5, right? But that's right around 5. Look at the table of values. Second table, and yeah, at 5, it's a 0. So instead of like going through some long list of the possible rational zeros, go to your calculator, find one. But then you need to divide it out because those last two, they could be anything. They could be irrational, they could be imaginary. And the only way you'll know is with quadratic formula. So you've got to reduce the polynomial to a quadratic so you can get the last two. So let's go through and do our synthetic division, right? So put 5 in the bracket, 1, negative 15, 75, and negative 125. Bring down a 1. 5 times 1 is 5. 5 times negative 10 is negative 50. 5 times 25 is 125. And sure enough, the remainder is 0. Right, so now we will say this is x squared minus 10x plus 25. And if I had to solve that, that's a pretty easy factor, right? That is x minus 5 squared. So x equals 5, right? Which is the 0 we already found. It just that 0, what we found now is that this function actually equals x minus 5 to the third, right? Because the 5 is occurring 3 times as a 0. Remember what we said about the graphs and the multiplicity? I mean, we would say 5 is the 0, multiplicity is 3. So what would we expect to see on the graph? Because it's an odd multiplicity, we expect to see it go through the axis when it hits the 0. Because it's going to change sign, right? It's not squared or to an even power. But it doesn't look exactly, most of our zeros are a little clearer. When they go through, they really go through, right? You know, this thing has more of the look of the cubic common function like that. Okay. Now this one had 8 possibilities, and we found the one that made it a lot easier. These things get a lot more complicated when you actually have a first number which has its own factors. I mean, just look at let's look at the possible complex zeros that we get with this one, right? They will be, if they're not complex, the possible rational zeros will be, right, the factors of negative 30 divided by the factors of 2. Okay, well, let's think. Factors of 30. 1, 2, 3, 5, 6, 10, 15, 30. Uh, 10 plus or minus 15 plus or minus 30. Okay, and what are the factors of 2? Plus or minus 1, plus or minus 2. Okay, now we have to take, which we didn't have to do on those first ones, we got to take all the possible combinations of the factors in the numerator and divided by the possible factors in the denominator. So it'll be 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, and 30 over 1. Then it'll be 1 over 2, and 2 over 2, and 3 over 2, and 5 over 2, and 6 over 2, and 7, 10, and 15, and 30 all over 2, which is going to be how many different zeros there? There's 1, 2, 3, 4, 5, 6, 7, 8 on the top, 2 in the bottom. That's 16, and they're all plus or minus. That's 32, right? Now, there will be some which kind of repeat. I mean, here's my list. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. That's the over 1. Now when I do the over 2, the first one, 1 over 2 is a half. Right? The second one is 2 over 2, but that's 1. That's already in our list. We wouldn't write it again. It's in our list. And then we do 3 over 2. That's new. 5 over 2, that's new. 6 over 2 is 3, we've got that already. 10 over 2 is 5, we've got that already. 15 over 2, that's new. And 30 over 2 is 15, and we've got it already. So actually, we were able to, like, there's a little efficiencies there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24. But again, we don't want to go through all that. Go to your calculator. Clear. 2x to the 4th minus 9x to the 3rd minus 18x squared squared plus 71x minus 30. Hopefully I put all that in right. Now I'm going to hit the graph. And this is a 4th degree polynomial. I can see 4 zeros, 4 x-intercepts, right? 1, 2, 3, 4. 3 of them look like they're probably integers, right? One of them looks like it might be in between the 0 and the 1. Let's go like that. Table of values. And scroll up for the one that was most negative. Yeah, there you go. Negative 3, 2, and 5. And then there was also one in between 0 and 1. Remember the intermediate value theorem? In between 0 and 1, it changes sign. So there was one in between there. In fact, if I go to the graph, let me zoom. Zoom. Come on. Zoom 2. Yeah, it looks like it's at a half. And, you know, there's a pretty good chance of that because that's definitely in our list right there. So I'm going to do the half just to show. The fact is there's no point reducing this whole thing because we've already found all of our 4 zeros. Okay. So let's do the 1/2 and show how it works. 2, negative 9, come on, negative 18, 71, negative 30, with 1/2, bring down to 2. 1/2 times 2 is 1. 1/2 times negative 8 is negative 4. Is that right? Yep. 1/2 times negative 22 is negative 11. And 1/2 times 60 is 30. And there you go. So that one in the middle is 1/2. Didn't show up in the table of values, but I confirmed it. The other 3 we could see in the table of values. Okay. Okay. Now, when it says find all the real solutions, that means we're not just limiting ourselves to rational zeros anymore, right? We have to find irrational zeros too. So let's see. Our first step could be to list all the possible rational zeros, but it's probably going to be to put it in the calculator. See if you could find one. All right, so let's do that. Y equals, clear, x to the 3rd minus 4 x squared minus 50. Oh, that was a plus 4. See how I messed that up? Okay, minus 15x. Come on. Minus 18. You know, and we really count on this being on the graph, a rational zero that shows up on the graph, because otherwise, how are we going to reduce it from a 3rd degree to a 2nd degree? it looks like it's -1, right? And I confirm it by looking in the table of values, -1, 0. So there's my 0. So use the 1 from the graph, right? And would -1 be in the list possible rational zeros? Sure. You know, the factors of 18 include 1, and that's got 1. 1 over 1 is 1. So from the graph, x equals -1 is 0. So here we go. -1. See, we got 1, 4, -15, -18. Bring down a 1. -1 times 1. -1 times 3. -1 times -18. 0. Okay, there's our remainder, which we expected. And now we've got x squared plus 3x minus 18. Okay, is that factorable? It is factorable, right? What are the factors? X, -3, +6, because that's a positive, right? So it's x plus 6 times x minus 3. So the last two, which happen to be rational zeros, x equals -6 and x equals 3. And because I was zoomed in, right, I didn't see those. Otherwise, I would have seen them. But I was zoomed in and I saw the -1. That's too easy. Let's see what's left. Okay, good. Okay, complex zeros occur in conjugate pairs, meaning if a plus bi is the solution, so is a minus bi, right? And why is that? Right? Because where do we get those complex zeros? Or the imaginary zeros? They come from the quadratic formula, right? You would never just have a plus I. You would have to have the minus I too. You'd have to have two values, which everything else is the same, except that plus changes to a minus. And that's the definition of conjugate. Just change the sign in between. So if we ever get 1, 0, which is a complex number, you're always going to get the conjugate, which is, although, you know, they're playing kind of, we ought to say imaginary. And they say that here where b does not equal 0. So it definitely means you've got an I term. You know, and the one thing they didn't say on this, it doesn't say there, I didn't see it in any other thing that they put in there. It's also the same thing with radicals. Like if you had 2 plus the square root of 3 as one solution, you would have to have 2 minus the square root of 3. Because where's that square root coming from? Right there. That was something that came out of the quadratic formula. So this is going to help us just when we have to do that counting of like how many complex zeros do you have? How many real zeros do you have? How many imaginary zeros do you have? Well, you know for the imaginary, they're going to be in even numbers. It has to be 2, 4, 6, 8, 0, things like that. Okay. So that leads us to this kind of a problem, which we'll probably do a couple of. It says find a 4th degree polynomial with real coefficients that has the given zeros. Okay, so looking at the first one, right, they've given us 3 zeros. So how is it that this thing is going to be 4th degree? Well, look at one of the zeros is -7i. Well, if -7i is a 0, what's another 0? +7i. That's why it's going to be 4th degree, right? So we can add to the list 7i. Okay, so there's our 4 zeros. How do we turn those 4 zeros into linear factors so that we can find our polynomial? X minus, right? You just take the 0 and make it x minus to 0. So x minus 2, x minus -2 is x plus 2. Right? X minus negative 7i is x plus 7i, and x minus 7i. So now you have to multiply. And when you multiply, since you're always going to have two factors which are involving imaginary solutions, you need to multiply them together first, right? Don't choose to multiply like x plus 2 times x plus 7i. Because when you do these two, they're going to get rid of all the i's, and we want that, right? So first multiply these two and multiply these two. So let's see, x plus 7. This will be x squared minus 7xi plus 7xi, and positive 7 times negative 7 is negative 49, but then there's an I squared, so that'll make that plus 49, right? That's negative 49I squared. So that whole thing reduces to x squared plus 49. How about the x minus 2 times x plus 2? It's x squared minus 4, right? That's the factoring of a difference of squares. X squared minus 4. And so now you need to multiply those together, right? X to the 4th plus 49x squared minus 4x squared and negative 196. These two are like terms. X to the 4th plus 45x minus 196. Yeah, you're right. X squared. Thank you. And notice the wording of the problem, though. I mean, there is like a subtle distinction here, which is it says find the fourth degree polynomial with real coefficients. If you didn't say that real coefficients part, then that could mean you would end up something here that actually had I in the coefficients, and none of this would work, right? You don't necessarily have the conjugate pairs if you're allowed to have imaginary coefficients. Then you might just have one odd imaginary solution. Okay, let's see. We'll do one more because I know this is too much. But so if we're doing the second one, yes. If you're doing the second one, then 1 and 3 are zeros, and 4 minus I is a 0. What's another 0? 4 plus I, right? The complex conjugate. 4 plus I. Okay, how do we turn the zeros into factors? X minus, right? So it'll be x minus 1 times x minus 3 times x minus 4 minus I times x minus 4 plus I. And before I would take another step, actually they do it a little bit different in the book. But I've seen different ways. I've seen Mr. Lang does it a slightly different way. I prefer to do it the way I'm going to show you right now. You could look in the book and at least find, I think that they end up doing this like x minus, they do associative property, and they move the parentheses around the x minus 4 and the x minus 4 for some reason. So I'm going to write it like this. X minus 1 times x minus 3 times x minus 4 plus I, because the minus times the minus makes a plus, and x minus 4 minus I. Okay, now we've got to multiply two together, right? Which two are we going to multiply together? Those two and these two, right? This is easy, right? This is x squared minus 3x minus x makes minus 4x, and negative 1 times negative 3 is plus 3. Anybody can FOIL those two. Okay, now in order to multiply the trinomial in each set of parentheses here. I'm going to recommend that you use a grid like this. Okay? Yeah. On one axis, you're going to write one of the factors, x minus 4 plus I. And on the top, I will write x minus 4 minus I. And then I'm going to fill in the grid by multiplying what's at the left and at the top and filling in the grid. There should be 9 things that I make by multiplying 3 things times 3 things. It's just a way to keep straight all the multiplying you've got to do. All right, so let's look at this. X times x is x squared. X times negative 4 is negative 4x. X times negative I is negative xi. Negative 4 times x. Negative 4 times negative 4, 16. Negative 4 times negative I is positive 4i. Okay, I times x is positive ix. I times negative 4 is negative 4i. And then what is I times negative I? Negative I squared, but I squared is negative 1, so that is positive 1. Right? And it's negative I squared. Okay, when you do that, right, what you're going to find is all the imaginary terms cancel, right? This ix, positive ix, cancels with negative xi. The negative 4i cancels with positive 4i. And what's left is x squared minus 8x, and there's a 16 plus 1, 17. Right, but no more i's. Okay, now we still have to multiply these 3 terms times these 3 terms. And I'm just going to make another grid, right? Just go like this. Okay, the first term, x squared minus 4x plus 3, x squared minus 8x plus 17. Fill in the grid. X to the 4th minus 8x to the 3rd, 17x squared. It's negative 4x times x is minus 4x to the 3rd. Negative 4x times negative 8x is positive 32x squared. Negative 4x times 17 is negative 68x. 3 times x squared. 3 times negative 8x is negative 24x. And 3 times 17, 51. So I think I could write it all here. Right? You made your 9 terms, combine like terms. There's only one x to the 4th. How many x to the 3rds are there? Yeah, what is this? Negative 4x to the 3rd minus 8x to the 3rd. About negative 12x to the 3rd. And then how many x squareds are there? 1, 2, 3. So 3 plus 32 is 35. 35 plus 17 is 52. Negative 24 minus 68, negative 92, minus 92x, and then 51. So that's the answer. It's a lot of work, a lot of things to keep straight. And I'm not going to do the next one because I think we already saw what we need to see. Come on, don't do this to me again. There we go. Okay, I think this is the last kind of problem that we get in here. I can't remember, but see, find all the zeros. Find all the zeros if you know that 4i is 1. Okay, and I'm going to show you how they do this in the book. If 4i is a 0, what's another 0? Negative 4i, right? So you know if 4i is in there, so is negative 4i. And that means that you've got factors of x minus 4i and x plus 4i. And if I multiply those together, I'm going to get x squared plus 16. Right? They're conjugates, so they're just going to, the middle terms will cancel. The last term will be negative 4i times positive 4i, which is negative 16i squared, which is plus 16. Okay. What the book shows you to do from here is then they say, well, let's divide out. Since we know this polynomial is a factor of that polynomial, then divide it out. Right? And how are you going to divide it out? Can you do synthetic division? Remember, you only do synthetic division with linear factors. You have to do long division with this. Okay, so let's do long division. 3x to the third minus 2x squared plus 48x minus 32. And we're dividing by x squared plus 16, right? But what do you notice about x squared plus 16? It doesn't have an x term. Remember, when you're missing powers of x, you've got to fill in. That even means on the outside, too. So we're going to divide by x squared plus 0x plus 16. So fill in for the missing power of x, and then do your long division. Right? What do I multiply times x squared to get 3x to the third? 3x, right? So that's 3x to the third and plus 0x squared. Subtract. Negative 2x squared minus 0 is negative 2x squared plus 40. What's wrong with this here? What's that? Oh, yeah, that's it. I knew I did something wrong. I was staring at that going, what did I do wrong? Okay, let me take that back. I jumped the gun. Okay, we still got to do the 3x times 16, which makes 48x. Okay, that looks better. Subtract. The 48x's cancel, right? That's 0x. And then this gives us our negative 2x squared. Now we bring down the negative 32. Okay, what do I multiply times x squared to get negative 2x squared? Minus 2. So that'll give us negative 2x squared plus negative 2 times 0 is 0. And negative 2 times 16 is minus 32. Subtract 0. Okay, so we expected that. We came up with that as a factor because we knew both of those were zeros. So this is your last factor. All right. So what is the last 0? 2/3, right? So x, therefore, x equals 2/3. I just set that equal to 0 and solve. Add 2, divide by 3, 2/3. You know, you could have, you know, if you were really given this problem and weren't told exactly how to do it, I know what I would have done. I would have gone to the, put it in the calculator, look at the graph. It would have been in between, obviously, 0 and 1. I could have presumed from the factors of 32 over the factors of 3 that 2/3 might have been it. I could confirm with synthetic division. Done. You know, so you got a lot of options there. Okay. Okay. So write each function as the product of linear factors and list all the zeros. I'm going to do one, just one. Okay. I don't want to do that. Okay, let's just do the first one. It's on the screen. The way you're going to do this is put it in the calculator. y equals, clear, x to the fourth, x hat 4, plus 8x squared minus 9. Let's look at the calc, zoom 6. You see anything? Looks like -1 and 1. You confirm in the table of values there. I've got it right there. Yeah, -1 and 1. So do synthetic division twice. Right. From the calculator, x equals 1, x equals -1. Okay, what are the coefficients I'm going to write down? 1, 0, 8, 0, -9, right? So this will, now I'll do the 1 first. 1 times 1 is 1. 1 times 1 is 1. 1 times 9 is 9. 1 times 9 is 9, 0. And now, do you remember how you do successive synthetic division? Just do it right away on that row of numbers, right? So 1 times -1 is -1. 1 times 0, -1 times 0 is 0. -1 times 9 is -9, 0. Right? So this is x squared plus 9. Right? Which you can solve for that. Just set it equal to 0. That's because there's no linear term. You just solve for the square and then take the square root. That's x squared equals -9. X equals plus or minus 3i. Okay, so there's our 4 zeros, right? 1, -1, 3i, and -3i. So when they say this, write each function as a product of linear factors, that means write it like this. I'm trying to carve out some space. X minus 1 times x plus 1 times x minus 3i times x plus 3i. Done. So you found the zeros, you write it as a product of linear factors. You know, and in this case, again, did you really make a list of possible rational zeros and all that stuff? No, and you probably wouldn't. Unless you're just asked specifically to do it. You know, you're probably going to go to the calculator and find those first zeros. So we won't do that. We won't do that. It just takes too long. There are a couple other rules that they have in there, which we're not going to use because, again, we're not going to do, you know, reams of synthetic division to find our zeros. But there are some useful things that we used to have to do this with. One of them was called Descartes' rule of signs. In Descartes' rule of signs, it says the number of positive real zeros of f is either equal to the number of variations of sign of f of x or less than that by an even integer. So for example, if you looked at something like this one here, this is the function. And how many changes of sign do you see? It was plus and then minus and then plus and then minus. So that means there's 1 change, 2 change, 3 change. So the number of real zeros, it's either 3 or less by an even number, 1. That's what Descartes' rule of signs says. And then if you want to know the number of negative real zeros, then you do h of negative x. Well, h of negative x would turn that into a negative, but that would stay negative because it's squared. That would turn into a negative. And that was a constant, so that would stay negative. So there would be no changes of sign there, which means there could be no negative real zeros. Which means if you had a list of 32 possible rational zeros, there'd be no point checking the negatives. They have to be positive. So that was useful in the time when you used to have to go over and over again to do that. Right? And then the upper and lower bound, that was an interesting one too. We used to get tested on this all the time. I just have to remember. if you do synthetic division, like here, and all of your coefficients with a positive number and all the coefficients are positive, it means there could be no greater number that's a zero. That's the rule of signs. And I think it's with a negative number if you get alternating signs, and there could be no number less than that number. But we're not going to mess with those because we're not going to do synthetic division over and over again. But those are, part of the history of it anyways. So we did use the fundamental theorem of algebra. We can list possible rational zeros. We understand complex zeros occur in conjugate pairs, and we can find zeros by factoring. That's the homework.